Okay, so let's talk about continuity, right? In continuity, we have three things that must be true. Okay, so anytime you're saying that a function is continuous, you have to have these three things. Okay, the number of one, I guess not number one, you can do them in any order you want to. But first, we need to make sure that the value is defined, right? The function actually has a y value at that x value. Okay, which means the y value actually exists, right? You have a y value for your given c. So we have an x value that we're calling c. So we have a point, right? There has to be a point there. It can't be a removable discontinuity. It can't be an asymptote. It can't be any one of those things. There must be an actual dot there. Number two, the limit has to exist. So the limit as x approaches c of your function exists. Right? So if the limit does not exist, then our function is not continuous at that point c. Right? The limit might exist at other places, but not necessarily at the point c. Okay, and then the third thing that has to be true, the y value has to be equal to the limit. Okay, the y value and the limit have to be the same thing. Okay, because there's functions that have a y value that has nothing to do with the limit, right? We've seen that already in this course, where we have graphs where the left and the right side approach 5, but at 5 the y value is 9 or something. Right, so we've seen those type of situations. So we need all three of them. The y value is there, the limit exists, and the limit and the y value are the same thing. Okay, so let's do some drawing. Let's sketch a function where f of c is not defined. Okay, not defined. So there's a couple of ways. You could have an asymptote. We could have a removable discontinuity, right? Something of that nature. Either one of those things will be fine to have in this graph. So our next one is where the limit does not exist. So there's a couple ways we can do that. So if this is my c value, right, I could have an asymptote at c where one side goes up and the other side goes down, right? That's a type where the limit does not exist on asymptotic behavior. Okay, or we could have a more traditional one where your graph goes to one point and then picks up and goes somewhere else, right? This is usually how we see our jump discontinuity for the limit not existing at some x value c. Okay, so anytime the limit from the left does not go to the same place as the limit from the right, these y values are different, then the limit there at that point does not exist. Okay, how about where c is defined, so we have a y value, the limit exists, but they're not the same thing, right? So this is where continuity fails. So here, we're definitely going to have some type of a hole in our graph, but that hole is going to be filled in with a y value somewhere else. Okay, the y value is somewhere other than at the limit. Okay, so the limit of this function is up here, right? This is the y value that the limit is going towards, but at that point, we have defined our y value to be something else, right? A removable discontinuity with that point somewhere else. And then what we want, continuous at some point c. Just make a nice pretty graph that you don't pick up your pencil for and call any one of these values c. And there we have a continuous function. Okay, so that's what we're going to be testing, is which one of these situations do we have. So we need to know the y value, we need to know the limit, and we're checking to see if the limit and the y value are the same things. Okay, so here are some discontinuities. Point discontinuity, we talked about this one where we have just a circle. Right, that's a point discontinuity. One thing is missing. The limit exists, but there's not a y value there. Okay, and a jump discontinuity, we have two separate y values somewhere far away from each other. Okay, so there's this big gap in between your y values. It can even be a small gap, but there's a gap in between your y values, which is where your jump discontinuity comes from. And then let's see, asymptotic discontinuity. So our graph approaches one asymptote on the left, and it can either go up or down on the other side, right? It doesn't really matter. But the asymptote, it makes you pick up your pencil when you're drawing this graph. Okay, physically when you are drawing it, you have to pick up your pencil and then put it down, bless you, somewhere else. Okay? Now, this is just a definition. There's nothing to do here. A point is said to be removable because the limit exists as it approaches a discontinuity. Okay, so this is your removable discontinuity. The limit does exist here. Okay, but these other ones, the limit does not exist as the x values approach those discontinuities. Okay, so you could say that we have endpoint continuity. A function is continuous at a left endpoint or a right endpoint if the limit as x approaches a from the left, right, your left endpoint of your function is the y value, or as the function approaches from the right, it is. So if the function limit and the y value are the same thing, then your function is continuous at the end points. Okay, so just something to be aware of. It doesn't come up very often, but it will come up once in a while. So this function, y'all, is something that we're going to become familiar with, I hope. Okay, this function of a square root of a quadratic that's being subtracted. Okay, you need to know that this function is a semicircle. This function is a semicircle. And because it's positive, it's the top half of your semicircle. Okay? So anytime we have a square root of something minus a square, right, let's just take a second and unpack this, shall we? So if we have y equals the square root of 25 minus x squared. Okay? If we were going to unsolve this, that means the first thing we would do is square both sides. Okay? Squaring both sides means we no longer have a radical. We have 25 minus x squared. Okay? And then our next step in unsolving would be to add x squared to both sides. And why would I do that? Well, most equations want both things on one side. X squared plus y squared equals 25. So if you remember anything about your conics, which I'm not saying that you do, so in case you don't, this is the equation for a circle centered at the origin. Okay, maybe you've seen this equation in geometry. Maybe you had a conics section unit in pre-calculus. That is your circle centered at the origin. X squared plus y squared equals 25. What's the radius of the circle, by the way? The radius is 5. Okay, so this graph of f of x equals square root of 25 minus x squared is the top half of our semicircle centered at the origin with a radius of 5. Okay, this one comes up a lot in calculus because they just love doing it. From -5 to +5, this is the interval. So our graph is a semicircle with a radius of 5. Okay, so be familiar with this equation. It graphs to a semicircle. Okay, so this is a continuous function on a closed interval, right? It's continuous on this interval because the endpoints have limits that equal the y values. Okay, that's what we're getting at here. It's an example of the previous theorem from the other page of notes. Okay, so our next one, find the value of x which the function is discontinuous. So where might our graph be discontinuous? Identified as a point, a jump, or an asymptotic discontinuity. Identify each value as removable or non-removable, as in, does the limit exist there? Okay, if the limit exists, then it is removable. And if the limit does not exist, it's non-removable. Okay, so the removability is all about the limit. If it is removable, redefine the function so that the value at that value, so it will be continuous. All right, so let's see what we have to do here. All right, our first function is this rational function, x minus 3. So what is our domain restriction? What number can x not be? Or x cannot be positive 3. If x is positive 3, then we have a 0 in the denominator, and our function is undefined. Okay, so we can think about this as being an asymptote to begin with. Okay, now it's going to be an asymptote if we can't reduce this function. Okay, so our first point is to try and reduce this function. So can we factor anything and divide out? Okay, so x squared minus 6 minus x minus 6 factors to x minus 3 and x plus 2. Okay, so we can in fact factor our numerator. So now we are able to divide out x minus 3 and x minus 3. So my graph is going to actually look like the graph of x plus 2, except for what's happening at positive 3. There's going to be a hole, right? It's undefined. So because we could factor and divide, right, our equation simplifies. That means we're going to have a removable discontinuity. Okay, removable because at x equals 2, we're going to have a limit, right? The limit does in fact exist there. Because as our graph approaches x equals 3 from the right, our y value is going to 5. Right, that's y equals 5. And as we approach it from the left, the y value is also going to 5. Okay, so because the limit as x approaches 3 of our function equals 5. So the limit does in fact exist, which makes this a removable point discontinuity, because it's only happening at one spot. Okay, only happening at one spot. Okay, so part B, this one is a true rational function. We have, once again, the domain restriction of x cannot be equal to 3, because then we have 1 over 0, and that is an undefined value. So we're going to come in here and put an asymptote, a potential asymptote, right? A potential asymptotic discontinuity. So x cannot equal 3. So this graph on the left side of positive 3 goes down to negative infinity. And the graph on the right side goes up to positive infinity, right? Because we can find the left-hand limit and the right-hand limit. So the limit as x approaches positive 3 from the left, right? So we'd plug in 2.9. And when we plug in 2.9, we notice that's a negative number. And if your solution is negative, your graph goes down to negative infinity. Okay? And then if you plug in the limit as x approaches 3 from the right, okay, that would mean like 3.1. Your denominator is a positive number, so it goes up to positive infinity. So here we have an asymptote. This is a true asymptotic discontinuity. Asymptotic discontinuity. There's so many vowels in there. Discontinuity. Okay, let's look at our square root function. Okay, what do you remember about square root functions? The square root cannot be negative, so x minus 1 must be greater than or equal to 0. Right? This is how we find our domain restriction for square roots. The radicand cannot be negative, which means x has to be bigger than or equal to 1. So this graph of our absolute value has been moved 1 unit to the right of the origin, and it opens to the right because it is a positive square root graph. Okay, so what type of continuity do we have here? Okay, so is this continuous at its endpoint? Yes, it is, right? So if we have 0, the limit as x approaches 0 from the right is the same as the y value there. Okay, so it can be continuous at the endpoint. So what do we have to do to our square root function in order for it to be continuous? And the answer is probably, what if we limit the domain? Okay, right now it says for all values of x, right? There's no restrictions. So let's put a restriction on it. What if we say for values of x greater than or equal to 1? Right? Let's put a domain restriction on our function and only look at values greater than or equal to 1. So no negatives, not allowed whatsoever. Okay, now is our function continuous to the right of positive 1? Yes, yes it is. So everything to the right of positive 1. So when we have one of these functions that has restrictions, right, stated explicitly, so it's continuous on all x values greater than or equal to 1. Okay, and we want it to be continuous. So let's only talk about where it is continuous. Okay, now these ones, this is the more fun variety, these piecewise functions. These are the ones that really get into, well, what are we going to do? All right, so we have the fence at, the restriction is at positive 1, right? That's where something interesting is happening. So we put in this quote-unquote asymptote here at positive 1. Okay, so we have everything less than positive 1. We're going to graph x plus 2. And everything to the right of positive 1, we're going to graph 2 minus x. Okay, so let's see what this looks like. X plus 2 crosses at positive 2, right? It has a y-intercept of positive 2 and a slope of 1. So 1 up and 1 over gets us to our less than, right? So we have an open circle where our graph touches x equals 1. Then we have a negative 1 slope going down this way. So this is the graph of x plus 2. Now let's graph the blue equation. Okay, it also has a y-intercept of 2, but that's outside of the domain, right? So we can only look at when x is greater than 1. So if we plug a 1 into here, 2 minus 1 is 1. So this graph starts at 1, 1 with an open circle, and it has a negative 1 slope. So down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. So what kind of a discontinuity do we have here? This is in fact a jump discontinuity. Discontinuity. There, I won't write all the words. This is a jump discontinuity because our y values are, quote unquote, far apart from each other, right? Literally, they're 2 units. So, all right, so we have a jump discontinuity. Is this removable or not removable? Not removable because the limit as x approaches 1 from the left of our function is positive 3, but the limit as x approaches 1 from the right of our function is positive 1. Okay, so the left limit and the right limit do not match up. Okay, but can we make them match up? If it is removable, oh, it's not removable, so that doesn't really matter. It's an unremovable because the limit there does not exist. But I could say, what if we changed our 2 to a 4 and we made this greater than or equal to? Okay, now would our graph be continuous? Right, because this point gets moved up 2 units. We moved our point up 2 units, and we made it solid, so then we would have basically a negative absolute value graph, if that were the case. Okay, so we could do some adjusting to our function in order to make it continuous. But it would be a little bit too much, I guess, for the function, too much changing for that to happen.
Mr. Richards?